Optical software allows engineers and designers to understand why a system works or how a system works. It allows them to understand why a system doesn't work if it's failing. It gives them the opportunity to try out new ideas, to understand how it can work better. We have the opportunity to look at new ways of doing things without actually having to produce hardware in advance. And so we can solve problems in software or on paper when changes are cheap and mistakes are easy to correct.
ASAP, the Advanced Systems Analysis Program for Optics, is a non-sequential ray tracing tool with over 20 years of commercial development, testing, and validation behind it. ASAP is an extremely powerful, realistic simulation tool for describing the behavior of optical systems. The world's top laboratories, universities, and corporations use ASAP to transform optical design concepts into working prototypes. ASAP is a non-sequential ray tracing tool which can also do sequential ray tracing. Sequential ray tracing is easier to understand. We typically think of light in an optical system moving from some sort of source to various optical elements in some purposeful order and arriving at a detector, maybe our eye or the film plate of a camera. But in reality, light can take many varied paths through the system, some of which are intended, some of which may be unintended or unexpected. ASAP excels in these non-sequential analyses where the order in which light interacts with elements is not known a priori.
ASAP is used by a wide variety of engineers. Obviously, optical engineers are prime users of ASAP, but also electrical engineers, mechanical engineers, chemical engineers, physicists, physicians all have need to use ASAP in some of their applications. Some of these applications include imaging system designs, projection system designs, illumination designs, architectural illumination, automotive illumination, bio-optical systems, aerospace and aeronautical engineering, many forms of mechanical engineering. Anytime you have an application where you need to control the delivery or the reception of light, you need to use ASAP. What sets ASAP apart from a lot of other optical codes is its universal applicability. I can do virtually any type of problem in ASAP, but what it gives me is the ability to handle the tough problems.
ASAP differs from other optical software that I'm familiar with because it doesn't anticipate how you might want to solve a problem, it lets you decide.
A really great modeling tool frees the engineer or scientist to implement his vision and explore it wherever it leads without any preconceived notions. This is what ASAP lets me do.
ASAP for me has been the best tool because it's been the most flexible tool that I've used, and I haven't found a problem yet that it couldn't solve.
ASAP is the arsenal of the optical engineer. It allows him to attack any optical analysis or design problem he may come across.
I find ASAP to be better than any other optical analysis tool that I've ever used. If I had to put my finger on the one thing that makes it the best tool that I've encountered, it would be no limits. It spans a huge variety of disciplines. Almost any problem that I throw at it, it's able to bring some sort of calculation or illumination to bear on the problem. If I have a wave optics problem, it can do wave optics. If I have a geometrical optics problem, it can do geometrical optics. If I have a radiometry problem, it can do radiometry. ASAP is fast, it's accurate, and it will solve almost any problem that I throw at it.